Thank you. Let me first start by thanking Natasha and Sergei for getting us together in this nice place. Let me also thank to the attendants which choose this talk instead of the beach. So, although I'm coming from Ljubljana, I will not talk about tantalum disulfide, but some completely other material. And I will talk mostly about magnetic dynamics. But despite this, I find kondo effect very important in these materials. It's not directly connected to our result, but it's implicitly very important. So let me start with brief overview. I mean, most of my knowledge about this effect is here, about kondo. So some 90 years ago, some well-known persons in physics reported on increase of resistivity at low temperature in some noble metal samples. And it took about 30 years for kondo to put together, to publish perturbative explanation of this effect, which is basically about scattering on paramagnetic or magnetic impurities in the sample. This gives logarithmic temperature term in the resistivity, which leads to upturn in the case of antiferromagnetic coupling of the impurity spin to the carrier spin. Of course, this does not diverge at low temperature, but with much more complicated theoretical consideration, one can find out that at zero temperature, actually conducting electrons form a singlet state with the impurity, leading to saturation of this increase at low temperature. So this is for very dilute case. This is true for very dilute case. When one starts to increase the density of magnetic impurities, as in this case, these singlets start to overlap and coherent transport is recovered at low temperature. However, and this can be seen as a kind of hybridization between the conducting electron strongly dispersive band with localized band of the localized spins, which leads to avoided crossing and hybridization gap. And depending on the position of the Fermi energy, this can be either kondo insulator or kondo metal. However, there is another interaction which competes with kondo screening, is RKKY interaction, which prefers ordered magnetic state. And as it was found by Donjah in '77, kondo interaction which is characterized by a single parameter, which is kondo temperature, depends exponentially on J and rho, while RKKY depends potentially. And this means that depending on this interaction, you will have either Fermi liquid kondo behavior, so this would lead to heavy Fermi behavior, or to some magnetic ordering, which is usually antiferromagnetic. So, cerium antimonite is member of a large family of rare earth monopnictides, and in this case magnetism wins in a quite spectacular way, with with magnetic phase diagram which contains 16 magnetic phases. All phases have in common that they consist of stacking of ferromagnetic 001 planes in different sequences, and at higher temperature there are also some planes which are non-magnetic. So the ground state is 4 sublattices antiferromagnet. If you heat the sample up, you have a series of very long period antiferromagnetic phases, but if you apply field at low temperature, you go through you have a couple of phase transition. First are two ferrimagnetic phases, so this is this one, and then above roughly a bit less than 4 Tesla, you would come into ferromagnetic phase. Also, this and then if you increase temperature, you have again ferromagnetic phases which contain these non-polarized planes. This is also, the transition is quite strongly coupled to transport properties, to electronic properties, and there is also weak coupling to the lattice, where the high temperature rock salt cubic structure becomes slightly tetragonal in the magnetically ordered states. So such phase diagram in principle looks quite interesting for optical impact, because one might hope that by optics one might introduce one more phase, so 70s maybe. Unfortunately, we had some technical difficulties, so I cannot report on such phase. Most of my results will be which we obtained were obtained in weak excitation regime where such things do not happen. But they are still quite interesting. So although this is quite old material, it was recently studied quite intensively by new techniques. One of them, of course, is ARPAS, where they actually in the magnetically ordered state, they found this strong hybridization between cerium F and antimon P bands around the gamma point. So still we see this heavy fermion effect quite strongly, while at X point this cerium antimonite, these cerium D bands show simple exchange splitting, so a kind of mixture of kondo and magnetic. There is also another work where they shown this really strong enhancement in mass, so quite strong heavy fermion effect. The band structure was much earlier also analyzed with in this ferrimagnetic and ferromagnetic states, also by coherent oscillations. And what can one learn from this is actually that there is quite strong coupling between electronic dispersion and magnetic order. What they also found is that there is some coupling to the lattice. So for example, in the ground state, this antiferromagnetic orders breaks actually induced additional periodicity in the system, which is reflected also in the lattice. This was observed in some X-ray diffraction peaks, but also one can see this strongly in the ARPAS, where you see, so this is paramagnetic phase band structure, and here you see strong effects of folding of the brilliant zone. So many bands fold back. So another important property of this compound is very strong anisotropy. So if one looks at the gamma center magnon, the gap is 4.2 millielectron volts, 4.2 millielectron volt, which would be roughly 40 Tesla. And when one does susceptibility or magnetization measurements at directions which are not exactly aligned with direction of magnetization, sample actually splits into domains. So basically, it's impossible to tilt magnetization away from the cubic axis. So some people also call it like Ising case, because you can only have up or down. To at least qualitatively understand physics of this compound, one needs to look at the cerium-3 electronic states. It's actually, cerium-3 is quite simple because it's only one electron in the f-orbitals. So you only have two manifolds, 7.5 and 5.5, and 5.5 is the ground state in the free ion. This is splitting because of spin orbit. when the ion is put into cubic crystal field, this manifold splits into two states. One is gamma 7, which is Kramer's doublet, and gamma 8 is 4 times the degenerate. So this Kramer's doublet is dominated by plus minus 3/2 Zeeman state. So of course, when system magnetically orders, these degeneracies are broken, and there is very little information how exactly this happens. It's quite clear that the ground state is very close to 5/2 because we know what is static magnetization of the sample. And this state, which is basically a Magnon state, is also seen in neutrons, but other states are not quite clear.
Sorry, so there's no trigonal distortion on top of the cubic crystal field?
I mean, basically, here it's magnetic. The tetragonal distortion would still keep some of this degenerate, but you have magnetically ordered state, which completely breaks all the degeneracies because you have magnetization. Yeah. So in tetragonal symmetry, only this 4 times degenerate state would split into 2 doubly degenerate. This contains both, first tetragonal plus, but this distortion is very small. Magnetic excitations, I've already mentioned this Magnon at gamma point, very large splitting. In antiferromagnetic phase, neutrons see also only one mode with similar gap at the gamma point. At that time, this is quite a long time ago, they concluded, yeah, we only have effective 2-level model, so there is no anisotropy, this might behave like Zeeman. But that is not true because we know that we have quite strong anisotropy in the static. So quite recent results, Raman scattering in the antiferromagnetic state, they observe additional excitations in addition to this 4.2 excitation, and they attributed it to some mixture of electronic and vibronic states. So let me go now to our experiment. So first of all, this is just sample characterization, just to check that sample is what we think. We see all the phases as in the field scan as well as in the temperature scan. So basically our technique of choice is to do pump probe, but to analyze so basically we take a crystal, we excite it and probe it by a light which propagates along 0, 0, 1 direction. We apply magnetic field along 1, 0, 0, nearly along 1, 0, 1, 0, 0 direction. And then we analyze the time dependence polarization properties of the probe light. And if we just take a look at the symmetries, we can see that we can have two main contributions. So one is polar Moche, which might not be linear because this is weakly tetragonal. And we have magnetic linear birefringence and dichroism, which gives basically sensitivity to the changes of magnetization along x direction. So this is longitudinal with respect. And there is possibility also to see transverse, but as soon as you have tetragonal symmetry, this will be quadratic. So the main contribution which you expect is due to the delta mx, so longitudinal. So here is the data at glance. So here I show two scans. Usually we cool in high magnetic fields to be sure that we have monodomain sample. So if we cool from the magnetically polarized paramagnetic state down, we see that we have this kind of single rise time signal, which becomes faster when we come into ferromagnetic states. And also what we see is presence of coherence oscillations in the ferromagnetic states. They appear exactly at this phase transition. So when we then decrease the field towards zero, towards antiferromagnetic ground state, we see that these oscillations cease in ferromagnetic phases, or at least they are not clearly seen and not reproducible. And then when we go into antiferromagnetic phase, we see change of the sign of the signal, and again we see a bit stronger coherent oscillations. On the long time scale, we see some slow relaxation, which we didn't really study in detail. So I will focus on this short time scale in my talk. And if we look at polarization, pro-polarization dependence, we actually see an isotropic signal consistent with basically delta mx, so longitudinal modulation of magnetization. So what is surprising is that if we look now in detail at the oscillations, is that in the ferromagnetic phase, we can fit most of the signal except this tiny exponential part with a simple displacive excitation coherent displacive excitation coherent oscillation model, which is usually used for phonons. So this is like I have a small cartoon. So you excite the system, equilibrium position is shifted, and then the coordinate which is relevant oscillates and returns back to this. So this was a bit surprising because this is magnetic system, and magnetization usually have a bit more complicated dynamics. Of course, this cannot be phonon because there is no phonons at this frequency range, and also the frequency has strong dependence on magnetic field. So it's definitely magnetic excitation. In antiferromagnetic phase, such fit is a bit difficult because oscillations are very weak, but still we can extract this oscillation, and we find basically two modes, one at 1.2 terahertz and one weaker one at roughly 1.4 terahertz. And these modes do not show any magnetic field dependence. Okay. So let me now first look at the ferromagnetic phase and try to see what this oscillation can, what is this mode which we see. At first we actually expected to see just a Magnon mode. So this means transverse excitation from 5-half to 3-half, which is also seen in neutrons. But we found that a frequency of our oscillation is almost 20% different than the neutron result. These are these blue squares. So it was not clear whether this is another excitation or maybe it's just some depolarizing field effect. So we checked this, we took the ferromagnetic formula, took the magnetization, and we noticed that basically this depolarization, which is consequence of that we are probing really a thin layer on top, is actually cannot give more than about 2% of shift. So this is definitely not the same excitation. Moreover, when we do the fits, we basically see that G factor is 4, which is quite different than what would be expected from the Magnon. So to understand what could this oscillation be, we do a symmetry analysis, and we see what kind of electronic state, basically these are band because this is ordered states, can be formed by this F states of cerium. And one can see that, and also we need to take into account that our excitation seems to be displacive. And displacive excitation is quite constrained in terms of symmetry. Basically, you can only excite modes which have the same symmetry as a ground state. And then if we look at the possibilities, we see that the ground state, which is 5-half, should have 2 E bar 2G symmetry, and there is another state minus 3-half which has the same symmetry. So this naturally leads to conclusion that oscillation that we see must be minus 3-half dominated. So together with a neutral result, we can put this first, the lowest excited levels. So we have 3-half, nearly 3-half. These of course are gamma states. So this is the local function which they are derived from. Is at 4.2 millielectron, while minus 3-half is at 4.7. So this is definitely very far away from any Zeeman splitting. Of course, there is a question where other states are, but we could not see them. So conclusion of this is that crystal effects remain strong and are quite clearly reflected on these excitations of these low-level magnetic excitonic excitations in the material. So how we can displaceably excite such an electronic state? Basically, because these two states are actually a linear combination of 5-half and minus 3-half, with ground state which is strongly weighted. And then when we excite conducting electrons, we actually change effective magnetic Hamiltonian abruptly. So basically we quench our Hamiltonian, but we don't change the symmetry. So this would mean that we would finish in a kind of excited state, and these oscillations are then just quantum evolution of evolution of the system with some occupation on the first excited state. Now let me now look also at the antiferromagnetic phase. So in the previous work, they did not very detailed analysis. They vaguely said, this is probably crystal field derived state, but coupled to phonons. So at first one would say, there is no magnetic field dependence, there surely must be phonons. But this is not really necessary, because we have quite a lot of backfolding of brilliant zones. So in principle, we can have many electronic states. And if you look at these 4 E bar 2G states, we actually have 4 states with the same symmetry, and if one of them is the ground state, then we can easily explain also this spectrum. And absence of magnetic field dependence can be reasoned from the fact that in the antiferromagnetic state we had this angular momentum flop. So basically sublattice magnetizations are perpendicular to the magnetic field, so effects should be quadratic in magnetic fields. On the other hand, we know that we have also backfolding of the of phonons, and if one looks at the phonon dispersion curves in this material, one actually, if we take into account quadrupling of the unit cell, there would be backfolding of phonons exactly in this frequency range. So it's also possible that these excitations are actually not magnetic, but actually purely lattice, or could be also a mixture. So unfortunately, we were not able really to disentangle this at this point. So maybe, do I still have some time? Not very much. So if we look then across the whole phase diagram, the signal is qualitatively very similar. The only difference which one can see is actually a difference in the rise time, which is much faster in the ferromagnetic phases. And this difference can be attributed to significantly different electronic structures of these phases, which are coupled of course, again, due to this condo effect to the magnetism. So let me finish by crediting the people. So most of experimental work was done by my former PhD student Mimoza Naseska, and the samples were from Nikolai, from our collaboration with Nikolai Zigadlo in Switzerland. And of course, I should mention the funding agencies. And maybe I can just put summaries for reading, but I will not repeat them. So thank you very much.